What is the consider? Everybody's ready? I'm like, Henry's online.
Yeah, Henry's there.
Oh,
Yeah. Oh, Henry's here.
Well, can you switch the display so it's the not the my notes and so forth?
Go up there where it says display settings right there. Swap presenter view and slide view.
Or duplicate slide view maybe?
Duplicate slide, yeah, duplicate slide. Doesn't look like it's
Add it here. It's not letting me click on anything here. Let me try. Hang on. Let me stop share. Let me try this again.
Can I start talking to you?
Yes. Yes. Yes, all the way up.
It should be up.
Okay, welcome to our special seminar. I'm going to talk just a little bit until we get the slides figured out. First of all, I'm super happy. Thank you for those of you that helped in the watershed this week. The seismic experiment, they're sledgehammering today. So the data looks pretty good apparently, and a lot of people are helping, so really appreciate it, including Adam, our visitor. So this is Adam Wlostowski. Did I say it correctly? Yeah. Because it starts with W, and he says you don't pronounce that, you pronounce the L, and it's like Wlostowski, so that's Wlostowski. Because otherwise, looking at the word, you wouldn't get to that particular pronunciation. And we're very happy to have Adam here. He got his PhD at UC Boulder, and he CU Boulder, yeah, that's right, sorry, CU Boulder, and he's working with Mike Kusa. And before that, you were a Penn Stater, and you got, I think you got a bachelor's and a master's in civil engineering. So we're welcoming him back. And just to give you a little bit of background, a couple of years ago when the CZO PIs did a strategic planning exercise facilitated by NSF, facilitated by someone by NSF, one of the things we decided that really would help us become more of a network was to fund a postdoc who would gather data across the CZOs and write a comparison paper. So that's what Adam is doing. And we decided that the data set that was the most right and the most comparable across CZOs was basically stream discharge. And so by working on stream discharge at all the different CZOs, we thought that Adam could start to walk the path of not only helping us compare our data for discharge, but also start to understand hydrologic conditions, which means when the water comes into the watershed, where does it go? Does it go back out to the T? Does it go out in stream flow? Does it become stored water? And so that's what he's trying to do, is use the critical zone knowledge to figure out hydrologic partitioning in the different CZOs. Now, he's not quite there. He's not going to be able to explain everything from the critical zone architecture point of view, but that's the path he's walking. This is about 1 year since he started. So he's going to show what he's learned about Shale Hills in comparison to the other, kind of where he's going for a first paper that's proving that synthesis and compilation. So did I do a decent job? He's a postdoc now, and he works for Noah Malach. She's a hydrologist at CU Boulder, and Karen Harmon, who's a hydrologist at Johns Hopkins. And he's been going to every CZO, so he probably knows more about stream discharge in all the CZOs than anybody else in the about. So welcome to Penn State.
Great, thank you.
And this is very interactive because it's all about, do we think we haven't told him something that he needs to know? Is he using the right data? Et cetera, et cetera.
Yeah, and to keep that interactive, encourage interruptions or questions. So the title of my talk, 100%, is hydrologic synthesis across the critical zone observatory network. And the purpose of this project, the purpose of the project is to make a first step towards a far more difficult task of understanding the coevolution of the critical zone function and structure. And so what I mean by coevolution advance slides.
Oh. Try that.
Yeah, great. So what I mean by coevolution is this idea that there is a bidirectional relationship between critical zone structure, defined crudely as above and below ground CZ architecture, and how that critical zone functions hydrologically. And by hydrologic function, we very simply mean the storage and release of water from the landscape. And so there are arrows going between both of these boxes because on the top, it is, I think, fairly intuitive to think about how structure influences hydrologic function. So things like the regolith depth and porosity of the critical zone are going to control how water is stored and the rates at which water is transmitted, right? Things like hydraulic conductivity, that parameters that describe how water moves, are controlled by structural features of the critical zone. But a far more difficult concept to think about and to quantify is how function interacts with structure. And this is often apparent over much longer time periods. And so, for example, the storage and transmission of water in the critical zone is a regulator of the rates of chemical and physical weathering that modify through time the structure of the critical zone. So this loop goes around and around through time, and that's what we could spend several careers thinking about and probably not completely understand still. And so because this is a postdoc for 2 years, and I don't have a career at the moment to devote to this postdoc, what I have been working on with my co-authors, Karen and Noah, is to quantify how sites across the CZO network store and release water. So the idea being that if we can devote our energy to synthesizing the hydrologic function of the critical zone network, that will provide a welcomed template for others within the community to help us think about the processes, timescales, mechanisms that can connect function back to structure. And so the objectives of the project and the objectives that I'm going to try to address today are twofold. One is to synthesize data from the network to identify mutually intelligible variations in hydrologic function. So this is an effort of hydrologic classification or taxonomy. And by mutually intelligible, that's very important. That's why this project was able to happen. We want to look at the same data sets in the same ways. So we're not scratching our head over how much of the results we're seeing are due to measuring something differently or measuring something in a different location. So we intentionally selected data sets that we can compare. From the results that we find from this first effort, we want to try to develop hypotheses that explain the observed variations in the hydrologic behavior of these sites. So that's what we're going to talk about moving forward. So this is a thoroughly cross-CZO study. I consider the core CZO network to be composed of 10 sites that are shown as dots on this map and are shown as bold letters. So you can find Shale Hills in purple here. The abbreviation SH refers to the CZO. And then at each CZO, we're studying one or several catchments. I have been looking at just the small Shale Hills catchment here, which also has the abbreviation SH. And so as we move forward throughout the talk, the color scheme that you see here is going to be consistently associated with CZO sites. So green, always going to be the Keogh, magenta will always be the Calhoun, and then to keep track of which site and which catchment the results are for. JEM and UJ, those two next to each other are the Hammett, the upper Harameo at Hammett, right? So you can follow the colors and the abbreviations to track them working. And so we're going to see data and results from 15 catchments spread across 10 critical zone observatories across the nation. It is apparent from this slide that there's a lot of diversity geomorphically in the catchments that we're looking at, right? They're all of different sizes. There's a whole range of elevations indicated by the colors here. And to reinforce that variability, I absolutely hate putting tables in the presentation, but I just wanted to kind of show this to illustrate the diversity in not only the morphology of these catchments as described by variation, catchment area, median elevation, relief, and slope, but also differences in dominant vegetation. Everything from tropical forests at Lukio to mostly a deciduous woodland here at Shale Hills, and then great contrast in the geologic parent material across the entire network. So a lot of variability, and so this makes this subset of catchments particularly ripe for doing cross-site studies with. So the first effort at all these sites was to collate data sets that we can compare and contrast. And so the data that I'm going to share with you from these sites today is stream flow shown for 6 water years at Shale Hills, shown in blue. In gray bars coming down from the top, 6 years of precipitation data from Shale Hills. On the bottom here, in the bright green, that's an estimate of potential evapotranspiration that was derived with the Penman-Monteith model. This darker green line that kind of shows up as a light gray is an estimate of actual evapotranspiration that is derived from scaling the potential evapotranspiration over the entire period of record by the difference between precipitation and discharge, with the assumption there being that what over 6 water years, what doesn't leave the stream or the catchment as stream flow is leaving as evapotranspiration, definitely an assumption. And to check how good we're doing through time with our estimates of evapotranspiration, I've plotted just for the years available here the flux tower estimating ET. And by and large, we're doing pretty good. There's lots of gaps in this data set and some odd things going on in water year 2011. But overall, this is a site where I feel like the actual ET estimates we have agree well with what the flux tower is estimating.
What was ETA again?
That's actual evapotranspiration. So there's potential evapotranspiration, basically the atmosphere demand.
You have to calculate, it's calculated.
It's calculated, that's right. So we took this PET time series, which is at a daily time step, and then we scaled all those values by the long-term difference between precipitation, the long-term ratio of precipitation to discharge, or difference between precipitation.
Didn't you say that there was the difference between precip and discharge?
So
you're assuming there's nothing leaving from groundwater.
that is the assumption.
And that's for ET sub A.
Yep. And the reason why we need to make these assumptions for ET when we're doing a catchment water balance is because ETA is very difficult to observe at representative spatial scales. Something like discharge is a flux out of the bottom of the catchment. So you can rest assured that if you're measuring all of the stream flow with your weir, that it is representative of everything leaving your watershed. You can scale precipitation across the watershed using some elevation lapse rate, which we've done, but ETA is very difficult to estimate or measure. You can measure it at a flux tower, but is the footprint of that flux tower representative of the entire catchment? That's debatable, certainly not. That's not always the case at all the sites. There's not flux towers at all the sites, and so we're left with needing to use a model to take an estimate of what actual evapotranspiration. Moving forward here, these screenshots didn't come out very well, but I just wanted to highlight what precipitation data sets and what stream flow data sets that I've been working with. So if you go on the CZO website and you look under Shale Hills data sets, I'm using this precipitation data set that Chris Duffy's name is adjacent to. And then the stream flow data set, Chris Duffy's name is also adjacent to. I work with Cheng to gap fill this record. And the stream flow data set, there are kind of many options to choose from for Shale Hills. A lot of them are basically reanalyses by using the PIM model to gap fill and make estimates of what stream flow would be when there's no observations. We just decided to stick with the observational period from 2006 to 2012. There seems to be a large gap in the record between 2012 and 2015. then there's data from 2015 through 2017 or so. But to avoid the headache of gaps and wanting a continuous block of record, these are the decisions we made. So
So 15, 12 to 15, is that when the year was down? That's essentially. Okay. And that change, are these the data that you're using to them? Is it consistent? Are we consistent? I mean, if anybody be able to talk about it.
I'm using some data. For precipitation, actually, I'm using the 2015 data. But for the model, what I'm using the analysis data from the national datasets. The reason is I want to keep that Shale fields and Canada have the same policy from different locations and measuring.
So you're not using the same data that you use on there. But I guess you should talk with Dan and Brandon to make sure these are the up-to-date data sets. But I know we went through that, but you know, like that. So.
Precipitation data, we definitely want to address. For streamflow data, the other option would be to use something that's
And then he also said that most of these data sets are all of them don't have DOIs, and we should, especially the ones he's using, we should get DOIs.
I know you're looking at me.
So that's something we need to think about.
Can I ask a quick question? So are you saying the ETA is calculated by Monash model?
ETA, potential evaporation, is calculated depending on season.
Okay, but as far as I know, the Monash model didn't take into canopy intersection into account. So if you're looking at the variation of the above ground physics architecture, so how can you take canopy structure into account if you just use Monash calculated value?
Sure. So the simple answer is that we haven't reduced our analysis to that level of complexity yet. So you can, kind of keep that in consideration as you move forward. So moving forward with all those similar data sets across the network, we can begin with basic quantifications and ask how much water is coming into and out of the catchments that we're looking at. If you're looking for shale hills on these spots, it's purple. On the top left, we have mean annual precipitation. The interannual variability, 2 standard deviations is shown as the bars. Similarly, mean annual runoff, the mean annual potential evapotranspiration shown as these larger gray bars, and the mean annual estimates of actual transpiration shown as darker bars. What stands out here are the green bars. That's the KEO. KEO moves an extraordinary amount of water through those catchments. Every year, the precipitation is in excess of 4,000 millimeters a year, which is just amazing. Swamped out the variability of the rest of the network. But then when looking within the continental United States, the Southern Sierra and the Eel River CZOs have a lot of precipitation. On the more arid end of the spectrum are Boulder and the Santa Catalina Mountains. Similar pattern is available present for variation in runoff across the network. And then here's what the distribution of potential and actual evapotranspiration look like. The reason why this isn't terribly informative is because it's often more insightful for hydrologists to think of the relative magnitudes of P to Q or Q to ET. And so what we can do as a follow-on is something called Fujiko partitioning. And this is a way of classifying across the network how water is partitioned at an annual time scale. And so let's focus on plot A here. Here I'm plotting annual runoff, Q, as a function of annual precipitation. So each data point there is one water year of information. The dashed line shows a one-to-one line. So if the data are applied really close to that dashed line in plot A, that means that the runoff ratio is equal to 1. All the precipitation coming in is leaving as stream flow. We can see is that the KEO, being the wettest of the catchments, the highest runoff ratios. And then everything else departs further away from that dashed one-to-one line as the annual precipitation gets less and less. These purple dots in here would be the shale hills catchment.
They look like they're the ones, the really low ones too. Right?
No, these are blue here.
Okay.
So this blue batch here is Reynolds Creek, Johnson Drop Batch. Now another way of plotting these data is to plot the 1 minus the annual runoff ratio, which if you make the assumption that what doesn't leave annual as stream flow is going to evapotranspiration, this could also be the evapotranspiration index. So 1 is that all the water is leaving to the atmosphere. 0 is that none is leaving to the atmosphere, it's all leaving from precipitation. And we plot that as a function of the aridity index. This is the ratio of potential evapotranspiration to annual precipitation. So as you move to the right on the x-axis, catchments are becoming more and more arid. So on the furthest right, this would be the Santa Catalina catchments, Marshall Gulch, and Oracle Ridge. And on the far left, bounding this space on the humid side, this is Luquillo, where the aridity index is less than 1. And then you can see that there is this first order relationship between how water is partitioned into stream flow or evapotranspiration. The stream flow data is what's informing this, so I plot it as 1 minus Q over P as a function of aridity. So as you become more arid, generally, you have lower runoff ratios, and as you decrease your aridity, getting down to the Luquillo, the runoff ratio is increasing, so we plot down here. And again, the runoff ratio of the Luquillo is very high, plotting close to that dash. And so this is all well and good for an annual perspective on how water is partitioned. So over the course of 1 water year, what fraction of precipitation goes where? We can answer with or draw estimates from this level of analysis. But what this doesn't do very well is provide a tremendous amount of information on the subannual filling and spilling of storage spaces. So what is the, on a day-to-day, month-to-month level, how is water entering and leaving the catchment that provides the patterns that we see here? In order to do that, we have to refine our temporal resolution analysis. So as a way of getting to that, we have created several, we've tried to identify the simplest possible models to characterize storage. And so the foundation of any watershed model, we're talking about Pim earlier, the Chang, one of the governing equations here is the conservation of mass in that model. Our model is just that governing equation. That is that changes in the total dynamic storage of a catchment or a cup are equal to the water that's coming in minus the water going out. With the case of a catchment, precipitation is entering from the atmosphere, and water is being returned to the atmosphere as evapotranspiration or leaving as stream flow. So this is a very, very simple model. So what that allows us to do is better synthesize data or information on discharge Q, evapotranspiration E, and precipitation P. Same color scheme for plotting these: precipitation blue, ET in green, precipitation is gray bars. We can use that equation from the last slide. We can switch things around and integrate such that the storage, the dynamic storage of the catchment is equal to the integration of P minus Q minus ET through time.
Is this Shale?
Yes, this is Shale. So if you haven't noticed, I try to build the examples of what we're doing on all the sites using data from your site. So you get a better idea. Yeah. Politics are important.
And you wear shirts from the school where they're giving
Sucking up. Okay. So what this allows us to do is take your data and interrogate it to see what the total storage radiation in the catchment is. That equation that this effort here, or this differential equation, requires some knowledge of initial conditions. We assume that the catchment storage state is starting at 0. And so what I'm plotting here are relative changes in catchment storage from some unknown initial condition, which we're just appointing to be 0. So the catchment starts at 0 storage, beginning first water year, and then we can run that equation forward in time using data to inform how storage changes. And so you can see that there's some clear annual variation that makes sense during the wetter parts of the year, the winter and the spring. Storage tends to be increasing, and then as ET ramps up throughout the late spring and into the summer and fall, storage decreases. The interannual behavior here is a general decreasing trend, but I encourage you to take that with a grain of salt, because one of the flaws of this model is that the uncertainty in storage is going to compound through time. So if you have uncertainty in P, uncertainty in Q, and uncertainty in ET, those are going to be compounding errors. And so I would say, generally speaking, that the interannual variation in storage is less believable than the annual patterns of spilling and complex.
And the dynamics of the total storage can be explained by deep drainage and groundwater exfiltration.
Because that is not considered in our model, if you have a very leaky system, that is going to affect what we see and could contribute to this interannual trend.
The shale hills, the barrel, above the barrel, above the intact barrel, we have the fracture system. So in shale hills, the deep drainage through the fracture system is very significant.
How much of that deep groundwater is then connected to the stream on a longer time scale?
So do you have data from groundwater wells or something that you could compare to check the mass balance? Does that work? It's the way of
Groundwater,
We've done a mass balance. I mean, like, we think that 90% goes out the stream and 10% goes out of groundwater. So, you know, that probably answers his question. I don't know if that answers your question.
yeah, I guess I'm trying to think if you can, is this a sort of secular drying out of the system over the last 6 years? Is it error? Is it the difference from not accounting for groundwater? Is there a way to unpack those things?
yeah. So is it a secular drying out of the system? Like that is like probably not. That's probably we're seeing in the interannual trend is probably a manifestation of the uncertainty in the data and water that we're using. But we can use other lines of information to give us a gut check on, say, the annual variability in water storage. And so wells would be one way to do that. The way that I've done it across all the CZO sites as just a gut check is to use data from the Plate Boundary Observatory Network, which are a network of GPS stations. And so throughout any given water year, as the landscape is filled with water, there is generally the mass of water in the Earth's crust subsides the Earth's surface slightly, and then as the landscape drains, water is leaving the critical zone, there's a deflection. And so here, for on top of the shale hills, I'm plotting the negative of the GPS anomaly, such that when the GPS anomalies are going upwards, because it's negative, that corresponds with potentially the landscape filling with water, and then the other direction it drains. This is what that correlation looks like, or lack thereof, at Shale Hills for the 5 nearest GPS sites with plate boundary observatories. This is kind of a regional scale confirmation. You can see that that interannual signal is not present in what the GPS data is showing. Assuming that all that deformation in GPS data is due to water storage. But at an annual time scale, our model is kind of corroborating what the GPS data is showing. But this is a kind of an estimate of total landscape storage. That's why we use GPS. If we were to use a well, the well would give us information on storage, but it wouldn't be sensitive to say storage water in Datos. So it is a subset of the total amount of water that is stored in the catchment. Because the well is only going to see the sash. This relationship is weakest at the end. It's significant at the annual timescale. Like if you do a correlation analysis, it's significant at the annual timescale at Shale Hills, and it is the worst relationship between GPS anomaly and total storage of the entire network. Places like the Southern Sierra and the Bill River, the relationship is remarkably strong.
So significant at the annual time scale, you mean the correlation between the black line and the GPS derived line is significant at the annual time scale?
We do a wavelength analysis to look over certain different time windows. The annual variation corroborates.
And your black line, you don't know where it really should go, right?
What do you mean by where it should go?
I thought you didn't know where the absolute level of storage was.
We don't.
You just know the trend, so it could be anywhere on there, right?
That's right. It doesn't matter. So when we're talking about dynamic storage, the only thing that matters is the relative magnitude. So the distance between the peak and the minima, that's meaningful. But if we took this whole line and shifted it way up here, that difference is still going to be the same, because everything is relative when we're talking about storage. What we're quantifying with water balance is not how much water is in the algae. We're quantifying how much change there is, how much I've drank today relative to, and that's to be differentiated strongly from the total amount of pore space that can hold water.
So is the correlation strength in California stronger because it's a more seasonal system, or is it because the T fluxes are higher?
So this is like pressing I'm not a geophysicist, so I don't know much about how this is inverted, but I think that the correlation strength from talking to some colleagues of mine in California is stronger because in Southern Sierra, the landscape is loaded in snow, a whole lot of it. So that wet season depression of the surface is the weight of snow weighing down the land surface. And it is also probably stronger because it's a Mediterranean climate. Yeah, the seasonal variability is more stark.
Yeah, two questions. Is this sort of slow descent that you see in Shale Hills, with, it being like potentially this, or somebody said this potential slow drying? Do you see that at all of the CZOs, or is this just?
It's just here.
Oh.
And like I said, the kind of the intra-annual trends could be a manifestation of the compounding of errors in data.
And then my other question is, you're saying that wells don't unpack the storage story enough because it doesn't account for data zone soil storage. But is there potential to use, like the soil moisture and other, I guess, like groundwater, water shortage data sets that we have in Shales to sort of start to unpack that? Or?
Absolutely. And as we continue throughout the talk, I'm going to show different ways of getting a little more specific as far as where this water might be stored. But kind of the holy grail of hydrology in a lot of ways is taking observations or inferences of storage at this scale and saying, unpacking it, saying this fraction is stored in Wlostowski, this fraction is stored in deep regolith or bedrock. We haven't gotten there yet, but hopefully by bringing this information out, we can raise questions across the network that can be answered using the data sets that are out there and haven't been included in this talk or this work so far. Cool.
Is our watershed the smallest watershed?
Second smallest.
Like the ZOB is smaller?
No, the ZOB is not included in this. The ZOB is within the lower Lahar catchment, which is way bigger than the ZOB. But the smallest one is watershed 4, which is smaller by 100th of a square kilometer.
And would you expect the error would be larger for smaller watersheds?
Smaller,
Smaller?
I would say, because with things like precipitation, the bigger the area, the more assumptions you have, the more difficult it is to assume that what precipitation is anywhere. Whereas, precipitation at the met station, how it goes there, probably pretty dark good estimate. So in an effort to unpack total storage, we can start with thinking about precipitation and make the acknowledgement that for these 6 years of precipitation data at Shale Hills, that not all precipitation is the same. And by not all precipitation is the same, I mean that the phase is different, and importantly so. A little bit of your precipitation likely falls as snow. Snow is shown as blue, and the gray is now indicating rainfall. And the implication of some of that precipitation falling as snow is that there is seasonal accumulation and ablation of snowpack across the landscape. It is not as significant of an accumulation here as it would be in the Southern Sierra, where their snowpack can get upwards of a meter of water equivalent storage. But the snowpack is basically acting as a temporary like a trust fund of water to the critical zone. So snow that is accumulated on the land surface is not immediately available for evapotranspiration, can't melt immediately, and be available for things like runoff generation and weathering. So it's basically on standby till it's melted and available for the sea.
Is this directly measured snow water equivalent, or is this inferred from some temperature and recent model?
Yeah, this is a model because importantly, Shale Hills is one of the only CZOs that has snow, but there are no observations of the snow. So if we want to do water balance analysis that accounts for the importance of snow, what we're left with at Shale Hills is an unconstrained modeling effort. But thankfully, the physics of snow modeling to first order, a temperature, a degree day model, temperature index model, which is what I've used here, and I'll talk about in a few slides, is what I've used. So these are estimates. If we had any additional information moving forward on snow water equivalent, so the snow scale on the station would start taking, we had estimates of snow depth. Just that little bit of information would heavily constrain this and help us tune what few knobs there are in this model to get this more correctly. Why snow is important is that when it melts, it changes the regime of precipitation delivery or water delivery to the critical zone. So this red here is what I'm calling terrestrial water input. So it is the sum of direct precipitation onto the landscape and snow melts. And you'll notice that, for instance, in 2008 to 2009, there was precipitation that likely fell as snow. I'm estimating it fell as snow from the model, but it didn't melt and enter the critical zone until a few months later because it was too cold and it was still on top of the landscape. And so what we can do with now this time series of terrestrial water input in the assistance of a snow model is we can refine our very simple black box storage model. And we can try to estimate dynamic terrestrial storage. That is what the water that's stored, likely to be stored below the ground surface. And so changes in terrestrial water storage are equal to the sum of melt and direct precipitation, so that's a terrestrial water input, minus Q minus T, right? So you see that the importance of a snow model, accounting for snow, is accounting for the delay of water delivery into the critical zone. So we differentiate this total dynamic storage into what we're calling terrestrial water storage by accounting for the influence of snow. So here's that snow model. This is how it works. So we inform the model with a time series of precipitation and a time series of air temperature observed at the site. We set rules about how the phase of precipitation is classified. It's an air temperature threshold, 0 to somewhere between 0 and 2 degrees centigrade is a pretty good estimate of when snow will start to fall instead of rain. And so that helps us figure out when snow is falling. And then the air temperature also helps us figure out the rate at which snow melts. So the model accumulates a snowpack, and then it ablates the snowpack with information coming from temperature index, not a full surface energy balance model. And then the output of the model is not only the accumulation of snow and the simulation of snow and the snow water equivalent of the landscape surface, but also when it melts, the model is simulating the rate at which it melts. And so that's the information that goes into these black bars here, which are the terrestrial water input. And you can see that every time this gray is going down, you have a melt flux is available to infiltrate into the ground. That's what the snow model is doing. That's how it works.
Will it be better to use hourly data than the daily data? Because maybe the average temperature of one day won't trigger snow melt, but if you look at the hourly data, maybe 4 or 5 hours of the day, the snow already begins to melt.
Yeah, that would be great, but hopefully we have hourly resolution precipitation, and hourly resolution runoff data. And at the moment, we've just decided to be uniform across all sites to work at the daily concept. But certainly within one day, you know, if you have a cold night and a warm afternoon, then yeah, you'll have a fraction of your time above zero. We're not capturing that. Okay, so back to this model. That's how the snow model works. The snow model is helping us resolve these two terms here, which gives us this terrestrial water. So we can differentiate now from total water storage by taking, I'm showing 2 water years of time, 2009, 2010, of Q and E and P. Now the snow model accumulates snow, figures out what the time series of terrestrial water input is going to be. And here is the gray bar of total storage, and the bolder gray bar is the terrestrial water storage. So you'll see that in the winter, as the snow is accumulating, your terrestrial water storage is depleting because there's some evapotranspiration taking water out of the ground, out of the critical zone, and all that water, there's water being stored on the surface. So total water storage goes up, the terrestrial water storage goes down until the snow melts, and then this gray line pops back up, and the total water storage and terrestrial water storage are similar when there's no snow on the ground, and then the snow starts accumulating again, terrestrial goes down. Here's your total water storage, maintaining a level above what the terrestrial water storage is, and then the ablation of snow, this big melt pulse pops up the terrestrial storage to create the total storage. Is everyone with me on differentiation between total and terrestrial storage?
Well, I'm kind of confused because you showed us another plot of storage that didn't look like this plot.
This is just a 2-year subset of the greater time series, just for illustrative. Okay. Now, what that allows us to do, this very simple conceptual model, is to quantify, make time series like this for all the CZO catchments for which we have similar data sets for. And we can look at the frequency distributions of terrestrial water storage. So each one of these violin-looking plots here is basically a mirrored histogram or mirrored probability density function that's showing the variation in terrestrial storage. And all of these have been adjusted to vary about the median, so they're varying about 0. They're adjusted by the median storage value. So they all oscillate about 0. Importantly, remember that when we're talking about dynamic storage, all things are relative. So it's about the distance between the top and bottom of these, not so much about their absolute magnitudes. And so you can see across the network, the colors now still correspond to where these sites are. Here are the abbreviations of the CZs in the catchments down here. And you can see there's a tremendous amount of variability in how wide these distributions are. And to reinforce that, these red dots show the interquartile range of each distribution. So some sites have these wide ranges of terrestrial storage. That means that the dynamic water level here, right, fills way up and spills way down. And you can sense that change in storage from the water balance. Whereas other sites, such as these two in the Santa Catalinas, they are the amount of filling and spilling that's going on in the critical zone there is much less than what's happening over at the Eel River and Southern Sierras. And I've arranged these from left to right, associated by their climatic orientation. So on the left here, these are arguably Mediterranean hydroclimatic regimes. In the middle, we have humid continental and subtropical climatic regimes. And then moving over to the right, these are sites that there is evidence in the data of there being some influence of the North American monsoon system. So how do we classify this, and can we get a little more quantitative about this? Yes, we can. So for each site, we have created these plots that for an average water year, October to October, this is the average annual variation, the black dashed line, average annual variation in terrestrial water input, that's water delivery to the critical zone. The green dashed lines are the average annual variation in potential evapotranspiration, on the left. And then these sinusoidal curves are model fits to the average annual variation that is present in the data. And so you can see a couple of things. Well, one first most apparent thing in these plots is that some places like the Eel River in the Southern Sierra, there's a big phase lag between peak water input and peak water demand. So supply and demand are strongly out of phase there. And we quantify a seasonality index, which I'm happy to get into the math later, but it's this parameter phi here. And when phi is negative, that means there's strong phase shift between water supply and water demand. As water supply and demand become more in phase, for example, at the Jemez or Boulder, or to a stronger extent, the Santa Catalinas, here, the North American monsoon, which shows up here at the Jemez, here in Boulder, that tends to shift the timing of water supply to be more coincident with the timing of water demand, potentially evapotranspiration. And so these sites will have phi values or seasonality indices that are positive numbers because the timings will co-align. If the seasonality index was 0, that means that there's very little precipitation, no variation in the annual regime of precipitation. For example, at Luquillo has a very small seasonality index. That's because this black line, while noisy, the average annual variation of terrestrial water input at Luquillo is very little. There's not a lot of seasonality. It kind of rains all the time. You're there in either the wet season or the wetter season. So it's really quite amazing. And so this is a way of being quantitative about the climatic zones that each of these sites are in. And so what we find falling out of this analysis of the seasonality index, now plotted on the x-axis, negative values to positive values, is that when you have Mediterranean climates with negative seasonality indices, these sites have very large ranges of dynamic storage. We're plotting the interquartile range, so the space between the red dots and those violet dots. This is the interquartile range of storage as a function of seasonality index. So when you have sites where all the water is arriving in the winter and then precipitation shuts off, and it's just evapotranspiration and stream flow draining the system throughout the rest of the water year, then you have a lot of filling and deep spilling. Contrarily, down at the sites affected by the North American monsoon, you're basically filling the cup at the same time that you're draining the cup. So its dynamic range of storage is relatively limited relative to what's going on for Mediterranean sites. And this relationship is significant, and I think fairly intuitive, but we'll get into it at the end. I think that the departures from this trend, or the variability around this trend, could be insightful to how the influence of critical zone architecture is acting as a second order control on partitioning or storage variability on top of just climate.
Which are the purple ones in Shale, the darker purple?
Okay, so yeah, a hypothesis could be that critical zone architecture may explain the residuals about this first order trend of climate control of the way water is stored. So that's one way of looking at storage. And the other way that we've interrogated storage is to think about what we call hydraulic storage. So hydraulic storage, let's just conceptualize it as this blue volume down here. Hydraulic storage is the water that is stored in the catchment and is responsible for the generation of stream flow. So certain places in the catchment that water is stored would not contribute to stream flow. Think about the Vado zone. When water is stored in unsaturated porous media, it typically does not move laterally. Stream flow generation has to come from saturated zones. It typically comes from saturated zones. The water can easily move laterally from down gradient towards a stream. And so the way that we quantify hydraulic storage is we start with the assumption that discharge is a function of hydraulic storage. So just like if I poked a hole in the bottom of my Nalgene here, if I had more water in this Nalgene, the flow rate out of the bottom would be greater than if I had less water, because it would be more hydraulic head on that hole when the cup is full, and less when it is less so full. You could take this expression here that just says Q is a function of storage. You could use a chain rule differentiation to express the rate of change in discharge with respect to time, as now using the chain rule to break that apart. Now it's dq by ds, the rate of change in stream flow to storage, and then the change in storage with respect to time. This first term here, we're going to call that G of Q. And that is it's importantly a sensitivity function. So when G of Q is high, stream flow is very sensitive to changes in storage. G of Q is low. That means that the stream is not very responsive to changes in this hydraulic storage term. And then the dSH by dt, this is the mass balance through time of the hydraulic storage. So this storage volume is being filled by recharge going down. It's being drained, obviously, by discharge leaving. Its primary role is to generate discharge. And then there is arguably a fraction of evapotranspiration that may be withdrawn from hydraulic storage. This alpha value specifies the fraction of total catchment evapotranspiration that might be leaving from these areas of the catchment that are active in generating runoff. It can vary between 0, that is, ET is not withdrawn from stream flow generating parts of the catchment, or it can be 1 in that all of the catchment evapotranspiration is being taken from areas of hydraulic storage. So moving forward here, we can rearrange this expression to solve for G of Q, and it is dQ by dSH. And what we find here is that it's minus dQ by dt, which is the recession rate of stream flow, divided by Q plus alpha ET, and that's just from rearranging this equation, with the caveat that we're going to look at that relationship in times when recharge is likely to be much, much less than discharge. That is, what's primarily changing the amount of hydraulic storage in the catchment is not recharge, it's drainage, either through stream flow or evapotranspiration. Once we have an expression for G of Q, this allows us to infer the hydraulic storage in the catchment by integrating the reciprocal of the sensitivity function from some initial Q to any value of Q as a function of Q. So those are the steps. That's complicated, so I've designed a way to just walk us through that so you can understand what I've done. Again, using data from Shale Hills. So here is single water year. I think this is 2011 at Shale Hills. Stream flow in blue, terrestrial water input as gray bars, evapotranspiration in green. This is actually just a couple months, not an entire 1 year. And so the first challenge is to find recession periods, so recession analysis. So we want to make sure that there's no snow on the ground, because here first of all, we're not even certain that there is snow on the ground, let alone being confident that it's not necessarily melting. So we just pretty much cut out winter recession periods, because there's a lot of uncertainty about if water is entering the subsurface. We also want to make sure that it is not raining for 24 hours, because part of the assumption here is that recharge is very, very low. So periods significantly after, or at least a day after a rain event, we're making the assumption that recharge is going to be relatively minimal. And then to give us sufficient information to determine dQ by dt, we want to make sure that the recession duration is at least 3 days. So you can see that these assumptions, or these limiting set of rules, limit a lot of the data. So a lot of the recession curves that you see aren't used. Only the ones in red are the ones for this couple of months that have passed our set of rules. Right? Thankfully, we have 6 years of record, so we're left with quite a bit of information. Once we have identified recession periods, now, for every recession period, we can quantify this term G of Q. That is, we can quantify the sensitivity and discharge to hydraulic storage, because recall on the right-hand side that it's equal to the recession rate divided by Q plus alpha ET. Make some assumptions about alpha, and put a pin in that, because we're going to explore the sensitivity of alpha towards the end of the talk. And so here, I'm plotting the net in log space, G of Q times Q as a function of Q. You'll see that there's a relationship that begins to emerge, right? And to make that relationship more apparent, we bin these black dots, which are individual quantifications of G of Q for every recession observation. We bin them to reduce the noise, and we fit a function, this black line, through here. So that's what's happening in step 2. The power of finding this relationship here is that I'm plotting G of Q times Q, a function of Q. And so G of Q then is this g of q q, which is given to us by this black line here, continuously as a function of q. And we just divide that by q itself, and we have an estimate now of what the catchment sensitivity is, the sensitivity of discharge to storage at every q, over the entire q range at Shale Hills. So the next step then is to take that function. This function gives us a function for g of q. We integrate the reciprocal of that function with respect to discharge, and that allows us to map a relationship between storage, hydraulic storage, and discharge. So the relationship at Shale Hills is shown here, and in red is what I'm calling the informed range. That is, our black line is only fit through a subset of the entire flow range. And then we extrapolate the relationship from here onto the entire range of flows. So this is fairly unhinged out here. So it's trusting that the relationship extends deeper into the range of flows. You can see that as hydraulic storage increases, discharge is increasing. Okay, that's kind of gut check number one, it should. Two is that it's nonlinear, right? So there are storage thresholds, whereas we exceed, say, 20 millimeters of hydraulic storage. Now the sensitivity of discharge to storage becomes more heightened, right? So you see a more rapid response in discharge to smaller variations or unit variations in storage. Now, once we have this relationship, that allows us to take the hydrograph shown in the top left, transform it through this relationship, and map or estimate variations in hydraulic storage. That is, we're using the storage-discharge relationship to transform a hydrograph to a time series of storage, and to be, I guess, judicious in some way, we've cut out flows that are greater than the 99th percentile flow over the record, just because those probably correspond to periods of time where there might be an overland flow catchment that is water bypassing storage. And so that's why you see chops here. And down here, that's when the discharge was reported as 0, so nothing shows up. Okay, so that's how we're estimating hydraulic storage for all the CZOs. So we take this time series of hydraulic storage. Well, I'll show you this first. This is this plot up here, these recession plots for all of the CZO sites. There's a really beautiful amount of variation in the shape and orientation of these recession plots across the network. It's something we're unpacking more in the paper, and describes this variation better is the parameters used to fit lines through these data. And they're just like awesomely different among catchments. And we're scratching our heads as to what might control that. But another thing you can see here is that the recession analysis works really well for some catchments and tends not to work well for other catchments. So Shale Hills, I would say that I think that's a pretty darn good fit to the recession observations. But the lower Lahara, I wouldn't trust that at all. Right? It's pretty much a garbage relationship, and I wouldn't say that the variation in the data is well captured by the fit that we use to put through there. In other places like Calhoun, there's only 2 water years of information, so there's a sparse amount of colored dots that is information derived from the data, and so I wouldn't say this line is very well informed. Contrarily, Southern Sierra, Eel and Elder Creek, Reynolds Creek, Boulder, the amount of variability described by the model in the black line is a lot higher. Right? So the recession analysis arguably works better at some sites, but not as well as others. From that, if we trust the information that's coming from the data here, and the assumptions in the analysis, we can plot or derive the relationship between hydraulic storage, which I'm plotting SH minus S naught, just to remind you that it's always relative to some unknown initial condition, which we would point to be 0, and then discharge is a function of that. And so here's the HEMAS at the Lahara, where the relationship is really bad. So it has a very serious shape here, sticks out like a sore thumb. I wouldn't put any trust in that. But the places where we have a moderate amount of trust, our method seems to work better at those sites. You can see that the storage-discharge relationships are all this kind of concave up shape here and express some degree of nonlinearity. They all look fairly similar from this perspective if you're not paying attention to the axes. But one thing that I find interesting about Shale Hills is that it, in the Calhoun watershed 4, have the lowest range of variability in hydraulic storage. So the hydraulic storage varies between 0 and say 30 millimeters at Shale Hills, and similarly at the Calhoun. And so what that leads to, we do a similar analysis like we did with the terrestrial storage for hydraulic storage. That is, we use these relationships to transform hydrographs into time series hydraulic storage. And then we look at the frequency distribution of the storage states. Here's the Calhoun, here's Shale Hills, tiny range of hydraulic storage variability compared to the range of hydraulic storage variability. Notably, it's really wide at the Southern Sierra, wide at the Eel River, Elder Creek. And so these catchments are grouped again from left to right according to their hydroclimatic orientation. And so that relationship, again, between the range or the interquartile range of storage, in this case it's the hydraulic storage, that is information derived from recession flows alone, has a negative relationship with the seasonality index. Not as good of a relationship as we saw with total storage, but there's arguably something there. These error bars I'm showing here, that's where that assumption about alpha is coming into play. So if we assume that all of the evapotranspiration and catchment is being withdrawn from hydraulic storage, that's the upper bound. If none is withdrawn from hydraulic storage, that's the lower bound. And so these error bars kind of give you a taste of where the assumptions about evaporation on recession flows are meaningful and where they might not be so meaningful. At Shale Hills, the error bar is actually within the dot. Right at the top of the screen. So.
No, so I was wondering, for the Sierra data, are you accounting for rain on snow events or dealing with snow at all? Does that change the hydraulic? How does that get partitioned to the hydraulics?
So we're being really conservative when it comes to snow because it's, rain on snow and frozen ground dynamics there's a capacity for the catchment to generate runoff by completely bypassing the ground itself. So we're interested in recessions because they contain information about how the landscape is draining its water. And so to be conservative about snow, to avoid these problems, we've just made a rule: if there's snow on the ground, we are just not going to look at recession flows from that time.
So then when you map it back onto the hydrograph, are you ignoring those periods as well?
No, we're not. And we're ignoring the high flows, but we're not ignoring those periods. That's a consideration.
I wonder if you have spikes, if you're extrapolating these high storage could be.
And then reaching out and artificially inflates the center. Yeah. I haven't done that. I should rerun and see if it changes things. So now I want to plot those two relationships side by side and just show that for each catchment, the range of hydraulic storage is always much less than the ranges of terrestrial storage. So this gives us some evidence that the water that is contributing to stream flow is involved in controlling the recession of stream flow hydrographs is a subset of the total amount of water stored dynamically in the catchment, which makes some intuitive sense. If you have water stored in the Beto zone, it is not contributing to runoff. So, for example, if at Boulder Creek during a monsoon season in Boulder, we could have an afternoon thunderstorm that does not generate flood. That's because the Beto zone is empty and waiting for water. It is stored in an unsaturated zone, and that water is not involved in generating runoff, unless, of course, the rainfall intensity is very high and you have a flood. The Beto zone is kind of gone. That water has to run in a lot of catchments in order to be hydrologically active. And so this provides us evidence that indeed this is a subset of the total amount of storage here. And my co-author here, Kieran, is really intrigued by how the range of variability in hydraulic storage from 200 millimeters down is much less than the range of variability in terrestrial storage across across the landscape. So although you have places that spill and fill upwards of a meter of water on an annual and intra-annual basis, the storage that's involved spilling and filling and generating stream flow is A, smaller, and B, relatively invariant across many different climates, which is interesting, and we have to dig into interesting explanations as to why that. So now to wrap up, the question that I always ask myself is, have we learned anything? The onset of this project, it could feel a bit like a fishing expedition. And if you don't catch anything, you don't learn anything usually. But I think that we have learned. And what have we learned? First of all, the climate is a first order control on the annual partitioning of precipitation across the CZO network. And that there's a tremendous amount of climatic variability expressed by the humidity index across the CZO network. And that, to first order, controls the way that water is partitioned at an annual time scale. And I hope that this is fruitful to the rest of the network, because this is the first time that we have put all of the CZO sites in the same state space with regards to their hydrology. We also use simple models to characterize dynamic storage state distributions across the network. And we've seen that there's an amazing amount of variability in the shapes, and more notably, the range of hydraulic and terrestrial storage variability across the network. And that, interestingly, I don't think it's terribly interesting myself, that hydroclimatic seasonality controls a lot of the variability in that dynamic storage state. So places that spill and fill under a Mediterranean climate have big ranges of dynamic storage variability compared to places in monsoonal climates where spilling and filling are happening at the same time. So moving forward, the kind of the pie in the sky goal of this project is to begin to align top-down storage inference, which is what I've talked about, with bottom-up understanding of the structure at each of these sites, right? So what we've done is, from a 20,000-foot view, said that here are how places differ, kind of at a crude scale, as to how they partition and store water. But what has been done already at many sites is this legacy of information of the bottom-up structural understanding of where water is stored and why it's stored there, for how long, has been conducted at different spatial and temporal scales. But I think that bringing these two things together is this is where the sweet spot is. We're not there yet, but because what we've done so far is just try to synthesize just this red bit here. But to completing this loop, the next phase of the project has to do more to integrate other data sets and other models to assist our learning from what we've shown here. So thank you for your attention and for being very gracious hosts. It's a privilege to visit Penn State again. Thank my group at CU, the hydrology group, landscape hydrology group, Hopkins. All the data is from the CZO network, some from USGS and NOAA, and the NSF supports this one. Thank you.
Thank you for your presentation. First of all, I have a suggestion. TWI is a little bit misleading because in hydrology, we often use TWI to represent topographic wetness index. So maybe better to call it in another term. The second question is, I'm trying to figure out the physical meaning of your G and Q. So can we use it to indicate the hydraulic connectivity of the CZ? Do you think that's a sensitivity between precipitation and discharge? So can we use it to indicate the hydraulic connectivity?
I think the first gap, so GQ is not the sensitivity of discharge to precip. It's the sensitivity of discharge to storage. That's generating.
Yeah.
I think that the first challenge is figuring out what is hydraulic storage, right? Like I showed you ranges and time series of hydraulic storage. but I can't go out to Shale Hills and say, there it is. Right? I can open up the subsurface, I can't point to it. So that is the first challenge that we need to get across, and that's the challenge that needs to be addressed and thought about more with all of this work, is that what we've done is we've inferred storage, and we put everything in black or at best gray boxes, and unpacking that into different subzones of the greater CZ. We need better models and better data sets to help us do it's possible. And yeah, I think
my point is, what does GFQ mean?
so it's the sensitivity of discharge to storage, and so it contains information about the recession rates of the stream.
Yeah, and your first slide, you're trying to link CZ structure to CZ function, and I think if we can link GFQ as an indicator of hydrologic connectivity, that can be a very promising way to build this linkage.
I agree. Do you have any suggestions on
Yeah,
some
one of my
suggestions
suggestions
variables?
Yes. One of my suggestions is, I think this indicator GFQ right now you're consider it as a constant for each CZ, but I also think it is a function of time.
But it's a function of discharge.
Yeah, but I think at least when you do the regression, you separate into dry season and wet season, because if we understand this indicator as hydraulic connectivity is very different between the dry season and wet season. It is quite related to the initial soil wetness condition.
So why don't we see if there's anybody else that has questions, and if not, we can break and have a one-on-one conversation or something like that.
Okay.
It sounds like you have a lot that you want to say. Are there other questions?
Yeah, so I thought that was
I don't want to cut you
really
off.
interesting. It showed the, sort of these, I guess, relationships between some storage and discharge, and we showed the relationship between CDS. But then you pointed out the storage at, Shale Hills and watershed 4, I think Calhoun were significantly smaller. Is that just a function of the size of the watershed? Like they're just small watersheds, they have no storage?
I think one hypothesis is that these places are structurally similar in that. So I know at watershed 4, you dig a pit. You've got this very sandy soil that's underlain by a really prominent BT horizon, lots of clays. It's not transient whatsoever, right? So you have perched water table dynamics where with a moderate intensity rainfall, you can't transmit water beneath that BT horizon before it saturates with this truncated A horizon and is shunted to stream flow. Right? In conversations with Stu, might be something similar occurring in Shale Hills, where from Chris Duffy, 90% of precipitation is shunted to the shallow subsurface. So maybe there's a permeability contrast near the shallow subsurface that is responsible for making discharge very sensitive to hydraulic storage. Because if you, it's a feedback. As you pond water up on an impermeable layer, it's going to intercept more and more permeable layers into the organic layer, which is therefore creating a more rapid response in discharge consequently.
So I was also wondering, as an extension of that, do you see, you've got a wide range of landscape areas across the different watersheds. Do you see that as sort of like a weakness of the project where you're trying to link climate to storage, or do you see it as a strength that you've got a range of areas?
I think it's a weakness. So if you look at the variability in the area, it's over several orders of magnitude, hundreds of square kilometers of the upper Sangamon IML versus much less than 1 square kilometer here at Shale Hills. So heterogeneity is going to manifest itself very differently in different size catchments. So there's relatively, think of how many Shale Hills it would take to fill in any one of those other catchments. And they're not all the same units, right? So you're going to have to contend with that. But our biggest catchment is also one of the most homogeneous catchments. The upper Sangamon is, from my understanding, I haven't been there, but it's completely cropped. It's underlain by tile drains, and uniformly so. But no, I think it's a short.
What's the minimum amount of time data you need to capture the dynamics of the system in terms of observational data?
Longer than we have here. So, so recall that assumption that I made about translation. Is that when we're in period record, that difference between P and Q is equal to the translation box. That's likely not appropriate at places where we don't have long periods of record. In most of these places, we don't have 10 years of record to work with. The shortest period of record is 2 water years at the Calvin, which is just where their CZO is. And so it's a discussion point and another point that an argument for longevity of the CZO is that if you want to begin to put the pieces of the puzzle together, it has to be a long-term study because it's very difficult to close a water balance in 2 water years. In fact, it's almost impossible.
So the challenge is closing the water budget, not necessarily capturing the full range of stochastic events.
And that too, we're 2 years of information. Are you looking at 2 years that are the exception to the mean or indicative of the mean behavior? And extreme events are very important to long-term. So could you be in a 6-year state of recovery in the last 1,000-year rainfall? You don't know. If you don't, that's why long records are wonderful.
But it sounds like even from just a year or two of record, we're capturing sort of the recession rate information that tells you a lot about sort of the key unknowns that vary between catchments.
Yeah, so I guess I'll hit my negativity there and say that the recession information, as long as you have enough recessions, it doesn't really matter how many water years you have. Where the length of record becomes really important is being confident in the long-term terrestrial storage. And the recession curves are a good one recession curve contains a lot of information. It's a unit, it's the recovery of a catchment from a unit input of water. Hydrology from unit hydrograph here. And it's things like the hydraulic connectivity of the subsurface, the transmissivity of the subsurface matter. Even with the short records, those hydrograms contain information.
So I think we probably should become informal now, just so that because people probably might have to leave. So let's thank Adam again, and anybody can say.
There's 2 more.
So Roman is in charge now.
All right, you can continue.